Hello, everyone. This is Spencer from Hydromantis, and I'm glad that you can join us today for our monthly webinar. Today, we're going to be talking about advanced process control and how and why GPSX is a good tool for being able to analyze different types of process control approaches and algorithms. And so today is going to be a little different than usual. I'm not going to focus quite so much on how to use the software as much as I'm going to try and focus a bit on how the different types of control are implemented and what that means for various performance issues at the plant. So as per usual, if you have any questions as I'm moving along through the webinar, please type them into the GoToWebinar questions box, which you should find on the dashboard there. And I've got that open up here on my screen and ready to go. So, when we get to the end of the webinar, I'll spend some time answering some questions. So anyway, let's move right along. So the plan for today is to just sort of talk a little bit of an introduction about process control and why modeling is a good way to analyze things. I'm going to then move on to different types of process control options that are in GPSX and just sort of briefly touch on the various ways that you can implement controllers. And then I'm going to run through 4 case studies. And these are basically different ways that you can do process control, and I'll sort of show you the interesting behaviors that you can see. To a certain degree, I've tried to make them sort of the same flavor. They're more or less the same plant in each case, and they're going to have the same influent running through the plant. So when we get to the end, we'll compare them a little bit, just a sort of a contrast, just to see how things turned out differently. But I hope you'll be able to see that different controllers have different focuses. They're trying to do different things, and so we'll take a sort of a little stroll through a couple of various options there. And lastly, we'll have a few summary thoughts, and then that's when I'll jump right into the questions and answers. Okay, so as I'm sure you know, being the modelers that you are, that models are really an excellent tool for analyzing wastewater treatment systems and specifically for testing process control on those systems. And there's lots of ways that you can implement a control in the models that we create. So you can have PID dynamic control loops. You can have timer controllers that activate at certain times on a sequence. And then you can have on-off or high-low controllers that can do various things. And of course, the most interesting aspect of these is when you're able to combine them together to do cascade control and get to really sort of sophisticated things that you can do. So really those controllers, as I mentioned, depends on really what you're trying to do. They can be implemented to improve plant performance, get to very low concentrations of effluent total nitrogen or total phosphorus, for example, or maybe improving your performance in your particular case is not necessarily getting really down as low as you can go, but maybe making your facility more robust. And maybe that's really where you need the controller for. A big one, of course, that we see all the time with the clients that we know that use GPSX is doing analysis where people are saying, how can I use control systems to reduce the amount of energy, particularly for aeration. And in general, controllers are designed there to just sort of make things run a little bit more consistently, to be able to have the model, to have the facility react to dynamic changes that are happening in the conditions of the plant, the loading that's coming in, or maybe there's other operational things that have to be done and the plant, needs to be able to respond to that kind of thing. So there's lots of different reasons why you might do control. So anyway, we're going to touch on a few of those as we go through our various case studies. The one thing I like about it, actually not only with controllers, but modeling in general, is really that you get to try out a bunch of different things and see what works the best. It's kind of like a screening, a bunch of different alternatives that you could do. The best part about modeling is that you can repeat the same thing over and over again while refining your approach. And it really allows you to do sort of an iterative approach and be able to relive some sort of dynamic event and say, well, what if we had done something differently? What if we'd had a different kind of control, when that wet weather event happened? So that allows you to sort of play around and redo things over again and compare different outcomes from the different types of controllers that you might be having to use. That ability to sort of have a test case where I'm going to make a challenging dynamic situation for my plant to be able to respond to, both in terms of operation and in terms of what kind of loading is coming through that plant. Those are really nice things to be able to do to get a good evaluation, and you can make as tough a test case as you like. So I've done that to a certain degree here today. Made a specific type of influent that we're going to test under a number of different types of control systems. Okay, so I'm going to touch right on now for the different kinds of control options that are available in GPSX. So if you've used the software for a while, you know that there's probably many different ways to implement a process controller in GPSX. And many of those are automatically already built into the menus of many of our unit process objects. So for example, when you drop a completely mixed bioreactor on our drawing board, it already has a DO controller built into it. And by default, it's actually turned on and set to 2 milligrams per liter. So those are things that are there for you to take advantage of. In a lot of cases, the controller is there, but it's not been specified. It's not been set up with its particular control variable or tuned, but they're there for you to be able to automatically take advantage of. So there's lots of flexibility available by using some of our, those existing controllers and also our generic controllers, which I'll show you in a moment. We have a panel called Process Control, and you can grab different types of controllers and put them on the drawing board, and then use those to be able to make a little bit more generic types of controls that can kind of do anything. And then this gives you the opportunity to play around and to do some more sophisticated work by combining all those things together. The last thing you could possibly do too is write your own control code. So as you know, GPSX is a very kind of open source system. So we still support the old Axle programming language. So if you have, a type of controller that you want to do and you want to be able to just simply put a bit of control idea behind something, it might not necessarily be a full-on dynamic PID control loop, but maybe you would like to say something like, when the flow is above a certain level, I want to do flow splitting in a certain kind of way, and at a different level, I'm going to split the flow a different way. That kind of algorithm, do something different during the weekdays versus the weekends. Those things can actually be nicely written out in Axle code, and if you go to our model customization tutorial, you'll be able to see how to do that. Now in version 8.0. Of GPSX that we released last year, we now actually support Python and Java as well. So you could use those languages if you prefer to be able to create your own control code and have it interact with the GPSX model. Okay, so I'm going to cover two options. One is using our built-in PID controllers, and then the other one is going to be using our generic controllers, both of which are just involved putting objects on the board and filling in some menus. Okay, so let's take a look at the built-in PID controllers. Basically, any place that you see a pump connection as part of the drawing of that unit process, that means that you're going to likely be able to find a PID control loop already built into this particular object. And they'll always be found in the operational input parameters menu. So go there and then open and then find the settings for that particular pump connection, and you'll see a blank controller code sitting here. You'll have the ability to turn it on and off and specify the set point. And then if you hit this more button, that's where we're going to go into all the details about what is the control variable, what kind of controller are we using, what's the tuning, and getting access to the tuning tool and all that kind of other stuff. So that's all available for you any place that you see one of these types of controller, pump symbols on there. They're available for almost everywhere you'll find them, and also for all the aeration systems. So almost any place that you see bubbles in the activated sludge tank, that means that there's an aeration system in that particular object, and if you go in there, you'll probably find a DO controller. I think actually it's every single one. I can't think of another one off the top of my head where we don't have a DO controller already built in there. And in most cases, you're just asked to set the DO set point, and we've already kind of tuned it for you. It's also available in the control splitter object. So I just want to touch on this real briefly because this is a very useful object in laying out your GPSX models. So this is a regular kind of splitter. It controls the flow, comes in one side, goes out. You in the control splitter, rather than setting a fraction, such as splitting it 50-50, you actually set the pump flow rate. So you set this side, the amount that goes through the pump side, and then all the rest of the flow goes the other way. The reason this is really useful for doing process control is it can be used as a way to control the wastage. You may find that rather than wasting directly off the clarifier, as typically we would do in most GPSX layouts, maybe you have to take that wastage and combine it with another clarifier, something that means that you can't use the controller that's built right into the clarifier. You can use this thing instead. So basically take all of your combined RAS and WAS together, and then you throw down one of these things, and you can use a controller that's already built into the wastage side and do that as well. This can also be used for doing influent flow bypassing as well, in much the same way. Okay, so that's sort of the way that they're built in. You can use them. It's just going to the menu, specifying a few things. You probably got to do a little bit of tuning, but generally that's going to work okay. The other option is to use one of these 5 controllers that are built into the system. And so for the case studies today, I've chose to do it this way, just sort of to make it very explicit how the controllers are working. And when you see them on the drawing board rather than hidden away in a menu, it kind of might help you to sort of visualize the way that this process control scheme is going to work. Okay, so you open up that panel and let's take a look at the first one. This is the PID controller. It's by default a feedback controller, although we do have the feed forward option there as well. But I'm going to talk about feedback today. And there you can click on that object, open up the controller settings menu, and then you will find similar parameters to what you would have seen in one of the ones where it was built into an operational parameters menu. There's one major difference here, though. This is a completely generic, sort of unspecified controller when you drop it on the drawing board. First of all, you don't actually hook it up to anything. It's sort of tempting when you see it on the board to actually want to make the flow go there, the thing that you want to control. You don't do that. You actually just let it sit by itself. I've seen very many people, and I tend to do this myself. I kind of either put it right next to the tank where I'm doing the control so that I can sort of see that's the controller, or sometimes if people have a lot of them, they'll kind of line them up along the bottom of the drawing board just to keep them out of the way. So it doesn't matter where it sits on the drawing board as long as you have it there. And then when you do, you have to specify not only the control variable, but also the manipulated variable. This generic thing doesn't know actually what it is you're trying to do, so you have to specify that detail. So first of all, you'll set this up by going into the More button and saying, this is the particular variable that I want to control, such as mixed liquor concentration. And then you'll set the set point, and then you've got to go in there and specify all the details about what it is you're trying to control. But you also have to set up this menu as well. So this is basically what is the manipulated variable. What is the thing that I'm adjusting in order to try and control that other parameter and get it to go to its set point. And in this case, you have to specify the cryptic variable name, and you can set mins and maxes and values like this one right here. Value of that variable. Sorry, this gets a little cut off on our menu when the controller is off. So basically what do you want it to do when it's not being used? That kind of thing. Okay. All right, so that's a PID controller. Now, the other one here that I use a fair bit too is this, what we call on-off controller, but it's probably more accurate to say that it's a high-low controller because you can also do things other than completely off. So the idea behind it, of course, is that you set a high and low band, and then your control variable will be controlled inside that group. So you have a value that's going to go up, and then when it hits this upper bound, that's when the controller activates and does something, and then that's going to hopefully cause it to stay inside this band and then move around. And you want to be able to control it, not specifically to a set point, but just within a band. So one obvious thing would be I could say I have effluent ammonia going up, and then when I get to a certain threshold, I say, you know what, I'm going to turn on more air, in which case that would theoretically cause your ammonia to come back down, and then I don't want to over aerate, so when it hits that lower bound, I'll back it off again. So you can have sort of high and low ammonia bounds, and then you would have correspondingly some high and low airflow rates to be able to do that. So again, since this is completely generic, you have to set both the control side, what is the signal that you are trying to control. And here's our high and low limits. And I'll mention just briefly while I'm here that this is in generic units here. So this is going to be in the generic units in GPSX. So it will be in SI units. If you ever have any questions about that, just email us and we'll tell you exactly how to set that up. And you have to specify the manipulated variable, very much the same thing. And here's the key part. Yeah, what is the manipulated variable value when the control variable hits that low limit, and what do you want it to be when it hits the high limit? And so that's how you set that up. And so you can use that in combination with other things too. Okay, this is the timer controller. And as you can see here, it basically is just something that is a repeating schedule over and over again. And so what the idea behind that is, you can just say, I have a cycle time, and I'm going to have it set to one value for part of the cycle and another value for other part of the cycle. And again, we've kind of taken an assumption here that it's something that will be on for a while and off for a while. That's why this is called the on time in one cycle. So this could be used for intermittent aeration. One of the case studies I'm going to show you in a bit is using this particular controller. The idea being, when it's on, what do I want the value of that control variable to be? So let's set it to some airflow number, and then the variable when it's off. And so this is, I could set it to 0, or I could set it to some low number or what have you. Okay, so those are different kinds of controllers that you can do. And then that same flow timer that same timer actually has a special flow timer version and a scheduler version. The scheduler version is actually basically just a whole bunch of combiners combined into one system. And you specify a whole series of phases that various things can turn on and off. And then you can specify certain flows and flow splits and any other settings that you want to do. This is getting into more advanced control, especially when you have a big complex layout where you're saying, I'm going to take this thing out of service and I'm going to do something else, or I have a really irregular schedule where, I only waste in the afternoons during the week and in the mornings on the weekend or something, those kinds of things. This is what you would use that for. I'm not going to deal with this one today, but just to let you know that it's there. It works like a timer controller. It essentially is, except you're doing multiple things together at the same time. Okay, so I'm not going to go into today a huge amount of detail about actually building something. What I'm going to encourage you to do is, if you want to know the details of like exactly what parameters you have to set and things you have to think about, where to get the cryptic variable name and all that kind of stuff. We've actually covered this quite a bit in previous videos and previous webinars, so I'll point you to our YouTube channel, and there are 3 particular videos that kind of cover all of that and in a lot of detail. And so I'm going to get on with our examples today. So the ones you should look at are, first of all, tutorial 7. So if you go to our YouTube channel and click on the videos section, tutorial 7 in version 8 is one that will go through all the details about how you set up a DO controller and a mixed liquor controller and so on. So that's sort of the basics of how to do it. We also have a couple of webinars that we've done in the past that talk about that in a little bit more detail than what's in the tutorial. So if you find this one here on how to configure MLSS and SRT controllers, that's there. And then the last one is, as I mentioned, this one from a little while ago, where we talked about modeling dynamic ammonia control in GPSX. So specifically, this is about doing different kinds of controllers. It's a somewhat similar one to what we're doing today. I'm going to go a little bit more detail today than what we did back then, but it's actually quite a good little webinar there where we compared different types of controls and what you get in terms of their energy usage and their performance. So, and again, it covers all the details about how to put that up. So if you come to the YouTube channel, click on the videos tab, and actually if you hit the little search bar inside our website there, our YouTube channel, and then type control, you'll be able to find all 3 of these right there. Okay, so let's take a look at these case studies. So as I mentioned before, the idea behind these case studies is that I want to sort of illustrate what types of controls can be done, what they look like, and what are the important aspects of this. So the different case studies are going to focus on different things. So they're going to be doing deliberately different jobs here. But I'm going to start out with a simple one, just doing controlling mixed liquor with a controller on the wastage flow. So the way that this is implemented is, and as I mentioned, I'm going to use this mixed liquor control generic controller there on the drawing board. So really what's happening in this case is I've specified that I want the mixed liquor, the concentration of solids coming out of that completely mixed activated sludge tank, I want that to be at a certain set point under dynamic conditions. So the controller gets a value for what that mixed liquor concentration is, and then it compares it to the set point, and then it makes some changes to the amount of wastage flow that is there. And it just does that at a regular interval, and it makes changes and onwards, and hopefully we can meet that. So I've got that set up here. And so what I'm going to do is, you can see here that I've already gone in and I've entered in all the relevant information here, and I'm going to set it for a 2,500 milligram per liter set point. So let's run over here and let's run a 7-day dynamic simulation. So first of all, I'll just really quickly sort of show you that what's happening in this particular plant is that we're going to run a 1-week simulation, and I've got a dynamic daily pattern happening here. However, also the daily average is also changing a little bit too. So what you'll see is 7 days with their daily peaks and so on, and I've made it pretty peaky. I want it to be challenging so that I can compare these things to each other a little bit. And I want to see a lot of controller action. So, but it's not the same pattern every single day here. You can see it's actually a little bit up and down, and there's some dynamics and interesting things happening there. So this is the same thing I'm going to use in all the other case studies as well. Okay, so now let's take a look at our controller. So we can see here that this wastage flow, so red is the set point that I was trying to achieve. That's 2,500 milligrams per liter. And the green line here, that just right along top of it, is basically the mixed liquor concentration as it's coming out. And we can see it sticks to that line pretty well. So in this case, we've tuned that controller, and this one is doing its job. And we can actually see the plot of the wastage flow going up and down over these 7 days. And so this is a reflection of what the loading was to the plant and how the dynamics of the flow and the dynamics of the loading and the amount of new biomass that we're growing are changing over that week. And so we can see some daily, a little bit of daily pattern to it, but also a little bit of swing back and forth as we were moving things up and down. And in this case, I would say that, I tuned this so that it was pretty tight and it sticks exactly around. If we were to, and it is possible to do it by just, turning up the gain and turning down the integral time a little bit, we could get this so that you practically can't even see the mixed liquor concentration underneath here. It'll actually fit it almost exactly. But that means, of course, it's doing much more changes in order to try and keep up with the dynamics of the model, and in which case this becomes really quite exaggerated and probably not very realistic at some point. So you'll want to find, of course, that nice middle ground somewhere between a very responsive controller that's doing its job, it gets to the set point quickly and stays there, but it doesn't also completely, overreact to the situation. And so it does not do sort of extreme pumping events, which would, of course, wear out your equipment and be bad for many other reasons. So anyway, that's what's going on here. And it's really interesting to see that we're going to hold this flat, pretty flat. And this is what was going on with the wastage. If I look at what the SRT of that plant was while it was running, we can see that because we're holding mixed liquor fairly flat, that it's actually, some variability in the SRT because we're kind of pinning down the mixed liquor and allowing the SRT to move around a little bit. So now, granted, this is an instantaneous calculation of SRT. It's basically just mass of solids in the reactor divided by how much we were wasting. So, of course, as the controller was moving the wastage amount up and down, it was, of course, the SRT calculation also varies a bit. So anyway, that's what's a mixed liquor controller looks like. And this is, of course, one that's behaving pretty nicely. Okay, moving on to same sort of thing, but we'll do an MLSS one. Sorry. Same thing, we'll do an SRT one. So very much the same concept. Instead of looking at the concentration of the mixed liquor, we can do it from the point of view of an SRT. So the SRT, the way I defined it was actually solids here divided by the amount of mass flow of wastage here. So we kind of need this whole bit of information. The controller would look at the SRT, I'm sorry, that's a little typo, that should say SRT control. And then what will happen is this will come down here and make some changes to the wastage in order to do that, in order to get that SRT to the set point that we have. A couple of things that are various ideas that you could do with this is, do I want to control only the aerobic SRT or possibly the total SRT? I guess it depends on the design of your plant. Now, this one that I'm showing you here, of course, is completely aerobic, but a lot of plants that are doing nitrification and denitrification, the total SRT of the plant includes everything. So you may want to just focus on how much do I want to control my aerobic part. So you need to just identify the aerobic SRT. I've also seen people thinking that instantaneous changes to SRT are probably not as important when you're trying to do control in dynamics, because of course that is that 5-day age of the biomass. So what they do is they do a 5-day moving average of SRT, and then they do the control on that, and then it makes everything run a little more smoothly. You may drift away a little bit from your set point, but the average all the time should be in the right place. So I will mention briefly that there is an instantaneous SRT controller built into the SRT definition menu. And in that case, we are not even doing a PID control loop. We're basically just calculating. We know exactly how much mass you have and what your flow rate is going to look like, or sorry, your concentration of sludge is. So we're just going to back calculate the amount that is needed to reach a certain SRT. And in that case, it's very much instantaneous and can bounce around quite a lot. But it's actually handy for doing design in that case. I don't really want to have to adjust the controller every single time I make a change to my tank size. So therefore, I'm just going to let the controller move. So that I'll just mention that one is there as well. Okay, so let's go take a wander over to the SRT control layout that I put together. So just to show you what the slight difference there, this is now SRT control. That means, of course, that I now have a different control variable up here. All this part is still the same, though, because I'm still using wastage. So let's run that one. Okay, so in this case, the red line is our SRT set point of 10 days. That was roughly equivalent to the mixed liquor number that, or sort of what the SRT of that plant was. If you remember, it kind of bounced around between, say, 8 and 12 or 13. Now we're actually going to try and stick it right at 10. And we're going to adjust the wastage to do the same thing. So now, instead of plotting MLSS, I'm plotting SRT. And you can see that there is that response to changes in daily, but rather than bouncing around and going way up here like it did last time, right now that's pretty tight between 9 and 11, and it's sort of doing its job there. Surprisingly, actually, the mixed liquor does not bounce around a great deal during that run there. So it's it's not even that much worse than having the mixed liquor controller on by itself. So the interesting aspect, of course, all these things are tied together, but in essence, controlling for SRT and controlling for mixed liquor are very similar kind of idea. And so that's basically what you would be looking at in this particular case. So we can actually see, we could maybe make this a little more challenging. We could maybe have some drift around to heavier loadings during the summer or those kinds of things. Nonetheless, it's a way to sort of evaluate what is the difference in the very subtle different aspects of changes between mixed liquor and SRT controllers. Okay, so let's go back to there. And as I mentioned, I guess I jumped ahead with this thought here that the SRT controller in a layout can, when you're doing design, like not modeling a plant that already exists, but working on a design, sometimes having an SRT controller can be really handy. That's the one thing I want to pin down and have it set for, say, 5 or 8 or 10 days or whatever's the number I want. Meanwhile, I'm actually moving other things around. I'm changing tank sizes, I'm changing aeration setups or whatever I'm doing, clarifiers and so on. But I can always make sure that I'm going to waste the correct amount for whatever size that I have by using an SRT controller, not for process control, but just to have one less degree of freedom to worry about. So. Okay, so that was case study 1, and I guess 1A and 1B. So now we have case study 2. So now I'm going to look at a different kind of controller. This is basically one that is going to do control on effluent nitrate. with a controller on the internal mixed liquor recycle. So first of all, this is a plant that now, as you can see, it's slightly different. We have a plug flow aerobic zone and we have an anoxic zone up at the front. So this is actually quite small in size compared to this. But in GPSX, of course, all the tanks look the same size. But we've added just a little bit of an anoxic zone at the front. And now we have, in addition to the RAS coming back and going in there, we have this internal recycle from the end of the aerobic zone into the front of the anoxic zone. And that's, of course, a MLE type process for the purposes of doing nitrification and denitrification. So one possible thing that you can do is actually control the nitrate by adjusting the rate at which we're bringing back nitrate from the end of the aerobic zone back into the anoxic zone, so we can denitrify over here with all of our bugs and with all that carbon coming in here. We'll take advantage of that sort of quote unquote free carbon that's available in the incoming influent wastewater and use that here. And so if we want to have a situation where we're going to have a predictable amount of nitrate removal, we could adjust this, turn it up when we need it more, turn it down when we don't need it, and therefore hopefully we won't use extra energy that we don't need. Okay, so we're looking at controlling this particular recycle flow, and we're doing that by adjusting and putting a controller on this particular pump. Okay, so the way it would work is we're going to look at the controller will look and get a signal on the nitrate concentration in that zone, and then it will make adjustments to the recycle rate. There's also various other options you could do as well, but let's, for argument's sake, say that we'll do it this way. Okay, so let's jump ahead and do that. Okay, so here, I didn't show you it before I went into simulation mode, but I will show you now. So we can now see that I'm controlling the recycle. I've got a set point of 5 milligrams per liter for nitrate in my anoxic zone. And so we'll see how that comes along when we do things here. And, we could do that on the effluent if we had thought. That's another option too. So right now we can see, again, the red is always the set point, and we can see the nitrate concentration bouncing up and down. It's pretty close to what we got for the set point here, but now it's dropping down, and we can see that the controller is actually recycling a bit less because we don't need to get rid of that much nitrate according to our set point. So it's going to back that off a little bit, and then continue along and make changes to this internal recycle flow based on what's happening in that particular reactor. So this is actually I've got a pretty tight sampling interval on this one. That's why it's running a little slower than the other ones. And of course, all of this has an effect on everything else that's going on in the system too. So I could look at the effluent the nitrate in the effluent. Is here we can see this is the total nitrogen. It's bouncing in and around sort of 7 or 8 milligrams per liter. Here we can see our ammonia is fully nitrifying. So we got lots of interesting nitrate to deal with, but we can see that signal is going up and down because the dynamics of the influent are happening, and then the controller's responding to that. Okay, so this basically is set up to do this. I played around quite a lot actually with the tuning of this controller. There's sort of a number of really interesting dynamics that you can get out of this. This is a relatively sort of slow reacting process. It's a lot different than wasting mixed liquor, because when you do that and you turn the pump up, the mixed liquor drops immediately. Of course, it takes longer to hold it back and grow that mixed liquor back again. But this kind of system here is all about the slowness of the growth of the heterotrophs in this anoxic zone. So you can see that it's a bit more sluggish. I even tried quite a bit more aggressive controller, but it would make really drastically crazy swings in the RAS rate and going much higher and lower than you would ever really want to. But then nonetheless, this is kind of giving us the typical behavior that we would like to be able to see. In a control, it's kind of keeping things in the right neighborhood, and it's doing its job. Okay, part of the reason why that's a bit of a challenge is that nitrate controllers are actually, really fighting a battle on two fronts. They're dealing with the fact that the nitrate concentration is dependent on two different things at the same time. One of them is the generation of new nitrate that's coming from nitrification. So if the amount of ammonia comes into the plant changes, then the amount of available nitrate that could be generated is also going to change as well. And at the same time, we're also trying to do denitrification by bringing back the appropriate amount of nitrate to that anoxic zone. So there's that balance. You're trying to hit that target, but at the same time, it's maybe generating more or generating a little bit less, or maybe it's denitrifying more or less, and the controller's trying to react to that. Of course, it doesn't know anything about how much is coming into the plant. And so it's a highly dynamic signal, actually. And I just took the screenshot just to illustrate that point. So if this is just this is just 2 days of simulation here. And we can see this nitrate, it kind of drops down, and then the recycle controller, does respond accordingly, and it moves that down, and that comes back again. And so, but here it drops again, and now it does exactly the same thing it was doing over here, but it didn't do anything. It keeps going down and down and down, and eventually it really, really drops right off. And then suddenly there's a big change. Well, what's the difference between what happened here and here? The reason is because this is sort of in the night when the loading went way down. And so therefore, we just did not have as much nitrate being generated. And so therefore, the controller said, oh, well, nitrate's going way down. I need to back everything off. I actually didn't have anything as much to do with the recycle as it did about the fact that the loading was different. So that's kind of a really interesting aspect of that controller behavior. Okay, so now case study 3, ammonia-based aeration control. So that's ABAC by a short name. And basically in this case, we want to be able to control effluent ammonia. This is not anything to deal with denitrification like the last one. This is primarily just about nitrification. Ammonia-based aeration control is there to try and hit a specific effluent ammonia concentration. And it's done with 2 controllers in series. It is a cascade controller. And in this case, we have an ammonia controller, which is looking at the concentration of ammonia in the system, and then a DO controller. And the ammonia controller controls the DO set point of the DO controller. That's why they're cascade in series. So what's happening is, for this particular setup that I have, is the ammonia controller gets a value for the ammonia, and it looks and compares to the set point. And then it makes a change to the DO control set point. And in this case, the DO control then looks into the tank and sees what is my DO control. How does that compare to that new set point now that I've been given? And then it makes changes to the aeration system and turns up or down the airflow correspondingly. So in this case, unlike the ones that the 3 that I previously showed you, this is a case where we now have 2 different controllers that each have their own sampling interval, the frequency with which changes are made by the controller, and also their own tuning and their own behavior. So it's quite a bit more going on here. And so we want to be able to sort of really see some interesting behavior out of that. And I've had quite a few people doing this in GPSX recently. I've given a fair bit of tech support to people, so I know that it's an interesting aspect that people out there are looking at. So let's look at this layout. Again, like I mentioned off the top of the webinar there, this is a case where you can take a model of a plant that you've already got, and then you can say, what would happen if we had this kind of control system? So. Okay, so let's take a quick look at the setup here before we get going on it. So this ammonia controller, in this case, is looking at the effluent over here, the effluent ammonia. We could choose to do it from, oh no, I'm sorry, this is actually the ammonia in the aeration basin. It's more or less going to be the same thing. So you've got that, and then we're changing the set point for the DO in the tank. So, all right. So now let's run this. Set that and get to the correct window here. Is this the one that I want? No, that's the effluent. I want the ammonia controller. Here we go. Okay, so now I'm just going to blow this up so we can see this clearly. So this is the results and the behavior of the ammonia controller. So this is the one that's looking at the set point for the ammonia, and then the green is the actual ammonia itself. So you can see in this particular case that actually the ammonia controller is doing its job. So despite big swings in the effluent, we're getting actually quite good response here. I think I've got this set for 0.35 milligrams per liter. of ammonia, so full nitrification happening in this particular case, and it's bouncing up and down here between maybe 0.3 and 0.5. So, that's really quite good control given the dynamic situation that we have. Okay, so now let's look at the DO control. And let's start out by looking at this first. So this is what's going on in the DO controller, and I actually kind of deliberately spread out the scale on this actually. So this is 0 to 5 milligrams per liter. So what's going on is we'll note for the first time in the webinar today, our red line, the DO set point, is not just a flat line moving across. It's actually dynamically being changed by that ammonia controller. And so in this case, the DO line is moving up and down and moving up and down as it responds to the performance of that plant. It's responding to how far this ammonia is drifting away from the set point. So the DO controller sees this new DO set point and it's reacting based on that. And so the green here is the dissolved oxygen and it's following along. I've got it tuned, I have to say, fairly aggressively in order to get this to work the way that I wanted it to, which is basically saying that I want the airflow to keep up with this DO set point. And and this is the airflow up here. You can see it swings back quite a lot in order to do that because we have a fairly challenging influent happening here. So this is moving along, and you can see here that the DO controller actually does a pretty good job. It's almost on top of the line most of the time. And so that is because I've got that set up with a fairly aggressive DO control happening. All right. So a couple of thoughts on setting up these ABAC controls. The sampling interval, the frequency with which that controller takes an action, is really important in ABAC. You have two different sampling intervals to think about. One of them is the ammonia controller, and one of them is for the DO controller. Now, the DO controller really needs to be able to react quickly because the ammonia controller is going to be consistently updating what the DO set point is. And so, therefore, you need to have the DO controller acting more frequently than the ammonia controller. And the reason is because you need that DO controller to have enough actions to catch up to the new thing that it's supposed to be doing. So you don't want it to sort of be lagging behind all the time. We want it to be able to get to its set point, quickly, do its job before that set point changes to something else, and then it's got to move it over to that point too. So generally, that loop, the DO control loop, has to act faster than the one for the ammonia control. And as part of that, of course, it's not just even the sampling interval, but also the tuning. So like some of the ones that I was discussing earlier, the tuning is super important to be able to get your controller, A, to do what you want it to do, but also not be hugely over aggressive and give you completely unrealistic and unreasonable results. So, so the tuning is really important, be able to keep it so that it's active, it does its job, it gets it to the set point quickly and stays there. But at the same point, don't give you like unrealistic, pumping actions or blower actions and valve control that wouldn't be really realistic in reality. Okay, so that was ABAC control. There's other variations that I've seen on this as well, where there's times that you can see maybe the signal for ammonia is taken from different places. You can even have different kinds of DO controllers. In the other webinar that I mentioned, we actually used an on-off controller, a high-low controller rather than a second PID loop here. That's also another variation that I've seen before. So it is a possibility to do kind of whatever you like by combining the various types of controllers together. Okay, so that's ABAC. So now we're on to the last one here, which is intermittent aeration control. So I've seen this at quite a few plants. It's certainly come up in several industrial wastewater situations that I've seen where you have very high loading or places where you need to do nitrification and denitrification, but I'm not really set up to have internal recycles or long plug flow systems that I can stick in an oxygen on the front. In this case, you have to do it by doing it in time, by turning on the air for a period of time and doing nitrification, and then by turning the air off and letting the DO be used up, and then you have an anoxic period, in which case you can do denitrification. And so it's a choice about how long you want those time periods to be and how frequently you want to cycle through that. And so therefore, because that's a choice, those things you don't want those things necessarily to be fixed. You want it, if you want to have good, performance, you can have a controller help you decide and keep the performance at a high level by making some changes to those lengths of those phases. And so that's really what I'm showing you here is a control of the effluent nitrate by doing it by controlling the time period that it spends in the anoxic phase and doing that with a DO controller. Now, in this case, we're doing 3 controllers in series. We have one that looks at the nitrate, sees, okay, is this close to our set point? And if not, then maybe I need to make the anoxic phase longer, for example. And then we have a timer controller that actually controls the phase. And then we have a DO control that makes sure it supplies enough airflow to get to the set points that we're telling it to. So just to summarize that, we have a nitrate controller that's going to look at nitrate concentration, and it's going to compare that to the set point that has been handed to it. It is then going to make a change to the timer controller to the length of time that it spends doing aeration and length of time that it spends being anoxic. And then that thing is going to look at where we're at, and it's going to say, you know what, we're supposed to be in an anoxic time, but I want to make sure the DO is 0. So then the DO controller is basically going to turn off the air. So we have nitrate controlling the timer controller. The timer controller passes DO set points into the aeration control system. Now, I could have put a third object out here, but I did it this way just for a little bit for brevity. Of course, there is a DO control system built in here, and that's the one that I'm using in this particular case. All right. So what ends up happening when you run this kind of system is you end up with alternating aeration, right? It's intermittent. It aerates for a while. This is the DO. The aerates for a while at, in this case, 1.5 milligrams per liter, then it goes down to 0. Then it goes back up and it goes down and up and down and up. What this controller is controlling is not the set point, 1.5 versus 2 or whatever. What it's controlling is this part. How long am I staying in that anoxic time? And that might need to be, smaller or bigger or whatever based on our dynamic load. Okay, this is just one way that you could potentially do, control of your system, but this is something that I've run into before and helped people set up. So I thought it was a very interesting example to do. Okay, so let's take a look at that one as our final example today. So I need this one. Before we get started, I want to show you this setup here. So just to make sure you're on board, we're looking at effluent nitrate here, and we're controlling the on time in this timer control. And what the timer control does is during that on time, it's going to set the DO set point to 1.5, and when it's off, it sets it to 0. So we have an anoxic time. And then this controller in here is the one that adjusts the airflow in order to meet those settings that are there. And that's just part of the regular, normal DO controller. And here's the DO set point. So that thing is just turned on like usual. All right, so let's run this one. And we'll take a look at what's going on here. So first of all, we can see, I'll just stop this for a second. We can see here that we've got our alternating aerating pattern here. So right now we can see that the DO is going up and it's coming down, and our airflow is going on and off as we would expect. So, so this is part of a day that I'm showing in this window, and it was scrolling by. So what I'm going to do is blow this one up here, and then I'm going to continue on. And what's happening now is if we look at our controller behavior, this is now looking at the nitrate controller, we can see again our set point. This is where we're trying to achieve here. And this is our effluent nitrate in green. And now we can see that the amount of time that we spend in the on time, the aerated part of the cycle is being changed. So in this particular case now, we want to, our nitrate is actually too high, so therefore we need to decrease the amount of time that we're spending. We need more anoxic time in order to do that denitrification. So it kind of wobbles back and forth between doing a little bit extra nitrification and maybe a little extra denitrification. but it kind of gets the job done this way, right? And it's only doing it, it's the same DO set points, just bouncing back and forth between 1.5 and 0, but it's doing it by maybe slightly longer periods of time and then backing off. And of course, that's responding to the changes in the load as well. And so there's lots of variations you could think about in terms of this type of behavior as well. I've seen systems that do this in a bit more sophisticated way in order to take advantage of doing sort of partial nitrification, doing nitritation, so you can get that first step of the nitrification process and land on nitrite and keep it there if you want. The AVN process is an example of that, where you might want to use this intermittent aeration in order to get it so that you can have a nice balance between ammonia and nitrite, and then feed that into an anammox reactor, and then sort of optimize that particular system and keep that under control, keep that in that right ratio there, so that the anammox system can be optimized for the best performance. Okay, so this is an example here. We can see that it's basically doing the job. It's kind of keeping this in the right neighborhood. It's making relatively small changes to the aeration time. And it's kind of hard to see on this front here, but sometimes these are a little closer together and sometimes they're a little farther apart based on what's going on here. All right, so I'm going to go back to my slides again. Okay. So again, the sampling interval, because we have controllers that are, in series, the sampling interval is again very important in that aeration, in setting up intermittent aeration control. In this case, the DO controller only has a very short period of time where it's going to act. In this particular case, based on some other examples that I have seen, I set it for 15 minutes. It's got 15 minutes to get it up from anoxic all the way up to whatever the DO set point is. In this case, it's 1.5. And so your DO controller needs to, like, when it's aerating time, it's got to come on quickly. It's got to get up to the right point and maintain it there until it tells time to set it back to 0 again. So actually, I had a little bit of period of time when I was making up this example where I didn't realize that I wasn't quite making it up there very quickly. This green line would sort of, at the beginning of the aeration phase, it kind of drag on and then eventually get there, and then it would drop to 0. And I was not really fully aerated in that sense. So what I had to do was make a fairly aggressive DO control, it had a very short sampling interval, and it had a very high gain in order to be able to get up here, so that when it was time to start aerating, it came on as quickly as it possibly could. So again, you don't want to make it overreacting in the sense that you don't want a huge spike here, red spike in airflow, and it's some unrealistic fashion, but here it's going up and it kind of balances off and then comes down again, and so on. So that's a really key element of this. Okay, to wind things up, I'm gonna maybe just compare these to each other. Now, I realize, first of all, I should say, I do realize that I'm kind of comparing apples and oranges here. Some of these controllers are designed to do one thing, and some of them are designed to do another thing. So there's not really any conclusion about what is better than something else. It is really just comparing what's really happening when I use these different types of control. So just keep that in mind. So first of all, you may remember that we had the mixed liquor control. That's where we started, and we're saying basically that we wanted to maintain a specific mixed liquor. In addition to that, I actually had the DO controller on too. So we know that it was set to 2 milligrams per liter, and we got an effluent fully nitrified. So all of our ammonia was down really low, and we had lots of nitrate. And basically, I used our operating cost part of the model. If you right click on an object and go to output variables, operating cost, you can get the amount of cost that we spent on energy to run this. So for 7 days, there's $231. Okay, SRT. More or less exactly the same kind of story. As you remember, there was a bit more different dynamics, but in essence, it put the whole system into roughly the same operating point. Now, if I had chosen a different SRT set point, then there would be a different story here. Maybe I would make it extra long or extra short, and things would change correspondingly. But for today's example, those two things were more or less pushed into the same operating place. Okay, so next was the nitrate internal mixed liquor recycle control. So this was one that was doing not only nitrification, but denitrification as well. And I will note that, of course, it was actually a slightly bigger plant than the previous two. And so, so in this case, yeah, you can see right away we did do nitrification and we did denitrification. We got it down to 5. This was actually our set point. We were trying to get it to 5. You'll note here that it's a little less energy being used here as well. Ammonia-based aeration control. So we had a way that we were now adjusting the DO set point, and the DO controller was moving along with that set point. So we didn't have one specific DO in the tank. It actually moved back and forth. In our particular example, it moved back and forth between 0.5 and 2, depending on the time of day and what the loading was. And we got full nitrification. We got some denitrification as we kind of passed through periods of low DO. We got maybe just a shade of simultaneous night denight happening there. And of course, because we were doing nice, turning things down when we could, we got some savings happening there as well. And then our intermittent control, where we were, specifically forcing it to go between 0 and 1.5 on a schedule, we were, of course, also doing nitrification and denitrification. So our ammonia was 0.6, not quite as good as the other control, but our DO and our effluent nitrate was 5, just like we were trying to set with the other one, and around a very similar kind of energy usage. Of course, these two stand out. When you're doing night and denight, you actually get some savings of energy cost, because some of the carbon that's coming in the front end of your plant is being used to do the denitrification. So therefore, you don't have to get rid of it in the aerobic zone. So you'll save a little bit of energy required there. Okay, so I'm going to get to winding things up here shortly. Oh, I meant to say off the top that today was going to be a 1-hour webinar instead of the usual 30 to 40 minutes. So in summary, there are many different types of process control schemes that you can build in GPSX using either our built-in controllers or those generic controllers that you put on the drawing board. And just I'll hit on that point again. When you're building those cascade controllers in series, pay attention to the intervals, the sampling intervals. Make sure that that inner loop, so to speak, the one that's doing the changes that are based on the other controller set point changes, make sure that that one's running faster and has a time to do its job before the next change happens. And as always, with any kind of control that you're doing, tuning your controllers is always hugely important. So nonetheless, I think that's it.